Well, good morning. Well, in the last class we considered motion in space. We told ourselves we are pushing ourselves in space, therefore we are trying to push forward, for which we have to give or provide a change of momentum. When we say change of momentum is what we call as impulse, and it has units of same as momentum, namely kilogram meter per second. We also considered what are the parameters by which we quantify motion. We told ourselves length is in terms of meter based on a standard, but ever since 1982 the standard is based on physical constant, which is the velocity of light in vacuum. We also told ourselves, well, mass is in kilograms, which is still based on the standard. Now current research efforts are on how to define a physical constant rather than an object by which I can define mass. It is still not done. When we say time, we say it is a period, and that period is second. When we say time is second, how do I define the direction of time? The direction of time comes from the second law of thermodynamics, which says that time progresses in the direction in which the entropy increases. Maybe we will try to take a look at it in the subsequent classes, because thermodynamics forms the basis of the entire rocket propulsion. Having defined these three quantities, we tell ourselves for change of momentum I need a velocity, and velocity is defined as meter per second. Distance is a vector, velocity is also therefore a vector. Therefore momentum p is equal to mass into velocity, therefore momentum p is also a vector, unit being kilogram meter per second. The question immediately arises, why use momentum when I can use velocity? See, the problem is momentum is a more fundamental quantity compared to velocity. The reason being, if I have an iron ball which travels at 1 meter per second and hits me, and I have a feather which travels at the same thing and hits me, feather does not lead to anything on me, whereas iron ball leads to this. Therefore in all subjects in which we deal with motion of molecules or classical mechanics, we deal with the quantity momentum rather than directly the velocity. The other quantity, as we saw, is acceleration, which is meter per second square. Therefore to be able to push and change the momentum, rather provide an impulse, we are talking of a change of momentum. And let us see whether we can define something properly, because we still have to reconcile ourselves that we are used to talking in terms of forces. If we talk in terms of forces, why do we have to talk in terms of momentum, velocity and all that? There must be some rational relation between them, and therefore we should go into this. But before I get into this, I want to bring out one example, and these examples are important, because when people talked in terms of going to the moon maybe some 2000 years back, what they had in mind was, maybe the sea is very rough, you have a lot of wave motion on the sea, and if in the sea there is a storm and there is a boat which is sailing, it gets caught in the storm, and because of the storm it is pushed forward. That means a large push is given, then perhaps from earth I can go to the moon. This was the first scientific article or first science fiction article which said how I go from the earth to the moon. The idea of being pushed up by a storm in the sea, namely when you have huge waves over the sea, that is huge tidal waves, such as when a storm occurs over sea, and a ship being pushed upwards towards the moon, was proposed by Lucian. He was a Greek philosopher who lived in the period, let us say around 40 BC or so. Therefore we are talking of something like push. Can I quantify push in terms of impulse, that is change of momentum, or rather call it in terms of change of momentum itself? Therefore, we tell ourselves, well, I am looking at maybe the momentum, which is a vector, maybe as a function of time. I have something like a body travelling at constant momentum, and maybe after over a short duration of time I change the momentum to a slightly larger value. And how do I change it? Maybe I change it gradually here, it has to go to the constant value and therefore it has to go like this. The period of change what I have here is a period delta t. That means I plot momentum as a function of time, and here I have the momentum changing from at time t it was pt, at time t plus delta t it is p t plus delta t is what is the momentum change. Therefore, what is the impulse associated with the change? The impulse is equal to the value of momentum at t plus delta t minus pt so much kilogram into meter per second, right. Therefore, let us be very clear about the definitions. Impulse is just a change of momentum. You give an impulse to a body, that means you change its momentum. And now, if I were to ask myself what is the rate of change of momentum? I want to plot the rate for this particular figure. How will the rate look like? Let us make a plot of this. We find that I have d p divided by dt. Now I plot as a function of time. I find that the momentum remains pt right from 0 to this particular time. In other words, pt is a constant, therefore dp by dt is 0 up to this particular point. Thereafter it increases, reaches a maximum, goes back to 0 here. In other words, over a period of delta t it increases, reaches maximum and comes back over here, and then after this momentum is a constant, and this is the signature what I should get for dp by dt as a function of time. Is it all right? Now I tell myself, I call rate of change of momentum as force. In other words, here I say this is my force. Then the force due to change of momentum is not something which is a constant, but keeps varying. Therefore, whenever I change the momentum and I ask myself what is the force, it is difficult for me to say how this force is going to vary with time. Therefore, what we say is, well, the force is continually varying during the change of momentum, and best for me to do is take an average value and say this is my average value, force is a vector, this is my average value, and then I say this is my average force. And whenever we talk of force, we mean something like an average value is what we call as force. Therefore, force is really a derived unit, it is not something fundamental like momentum, and we must keep in mind that the force during a particular change of momentum continually varies, but I take the average value, and what will this average value be? Let us put it down, f bar, and we say it is a vector again. I have reversed my thinking, anything will do here. Therefore, it is equal to, I talk in terms of maybe dp by dt is the momentary value, maybe I take it over the time dt or delta t, I integrate it over the time maybe from here to here over delta t is what will be my average value. That means I must also multiply over here by delta t, this must be, that is rate of change of momentum averaged over a period of delta t is what is force, or rather f bar is equal to 1 over delta t of the integral what I have written here to delta t of Therefore, you really see force is something which is not that good a unit compared to what we should say this, and if I have to write it in terms of impulse, how I should write it? This I can write it again as equal to, or impulse I can write I is equal to force into delta t, right, average value into delta t. This into delta t is the change of momentum and therefore impulse, and this is equal to, I have p t plus delta t minus p t over here. Is it all right? Because we find force is equal to this divided by delta t, or F into delta t is this, and the change of momentum is impulse, and therefore the correct connection between impulse, force and change of momentum comes from this particular equation. If we are very clear about it, having seen the parameters, we tell ourselves momentum is more primary than force. Maybe it is time for us to get into this universal law for gravitation. And what did we tell ourselves in the last class? We told ourselves, well, all planets as they go around the sun are all freely falling bodies, right. We told ourselves a planet, maybe Earth, is continually falling onto the sun, so also an apple is falling down, and this is the observation which Newton has, and he says a heavy body like the Earth attracts a body which is up in space, or maybe sun is attracting the Earth, and if I say this is the mass of the sun and this is mass of the Earth, he said, well, the force with which it attracts is given by a constant multiplied by the attracting body, the body which is attracted divided by r squared. In other words, why it should be the sun and the Earth? It could be any heavy body, let us say m1, attracting a small body, let us say m2, at a distance, let us say r, the distance between them is r over here, the distance is r over here, therefore the force is equal to m1 m2 divided by r squared into a constant, and this becomes the universal law for gravitation, and g becomes the universal gravitational constant. You know, this law is important, as we shall see in a moment or two. Therefore, let us rewrite it. You know, this the way I have written is cannot be correct, because force is a vector, r is a vector, m and m are masses. Therefore, I should have really written this as the force is equal to maybe a body 1 attracted towards 2, or let us say the body 2 attracted towards 1. Therefore, I have the body 2, which is a light body, being attracted by a heavy body m, goes as a gravitational constant into r square. Therefore, I put it as r is a vector to the power 3 mod of this vector into r bar, that means m1 m2 by r squared into g, and it is being attracted, therefore it is a negative sign. This is the universal law for gravitation, g is the gravitational constant, and therefore the unit for g should be what? It should have the units of force divided by kilogram square multiplied by radius square, right, or meter square. What is the unit for force then? We should be clear about it. What did we tell ourselves there? We told ourselves force is the rate of change of momentum, force is equal to dp by dt. Therefore, we are telling the units for force is equal to one over time divided by kilogram meter per second, which is equal to kilogram meter per second square, and this particular thing kilogram meter per second square is what we call as Newton. Therefore, the force has unit Newton, which is nothing but kilogram meter per second square. It comes from rate of change of momentum, and therefore, we have the units of g as Newton meter square by kilogram square, and the value is something like 6.671 into 10 to the power minus 11 Newton meter square by kilogram square. This is the constant in the universal law for gravitation. I think this is very important. Why I say this is important? Let's take a physical example. You know, I have been telling you that maybe in our solar system we had the 8 planets going around the sun. We also have some loose objects like asteroids which are also going around, but they do not have a well defined path or an elliptical orbit like what the planets have. You know, it is said that one of these asteroids is likely to hit the earth maybe in the year 1936, I am sorry 2036, and if it does not hit, maybe it may come back and again hit it in 2039. What is it we are talking of? Maybe some of these asteroids may come and collide with the earth. You know, we have been talking of these asteroids. These asteroids, when they enter the earth's atmosphere, they rapidly burn out. Therefore the question is, how do I make sure that an asteroid, let us say it is going around, it is going to come and hit it, how do I make sure that the asteroid is not going to hit it? What is the type of propulsion system, or how would I design my propulsion module such that I prevent the asteroid from hitting the earth? Can we think of it from the universal law for force over here? People talk of different strategies how to prevent some of these things happening, and let's try to solve this problem. It helps us in doing something with the universal law for gravitation. Let us say one of the thinking is, maybe this is our earth, maybe I launch a rocket onto space and I keep on accumulating satellites over here, I make a heavy mass over here, and when the asteroid comes over here, this mass being heavy compared to the mass of the asteroid over here will attract it towards this, and maybe instead of the asteroid going in this particular direction or in some particular direction, it will change the direction and it will miss the earth. This is known as a gravity tractor. That means I put a mass in space and make sure that this mass is near to the asteroid and the distance is small, it gets attracted towards it, and the asteroid, instead of coming like this, can get deflected away from this. You know, these are all possible, right? That means, you know, the law is not only for, let us say, conventionally doing problems in mechanics, but can be applied for changing the trajectories, and changing the trajectories is as good as giving some propulsion element to it. The gravitational force what we are talking of, or rather the gravitational field, is a weak force, and it persists over a very long distance. Like let us say I have the earth here, maybe a mass above the surface of the earth is attracted with a higher field than something which is maybe very far away, because the field decreases as the distance from the earth, the attractive field from the earth decreases as we progress away from the earth, as it were. Let us do one problem to be able to assess the gravitational field, and I take a model problem again of an asteroid, and let us calculate what is the force exerted maybe by this asteroid on something which is moving near it. I think this will tell us what is the magnitude of the gravitational field for some space related problems. Let's do this problem. I make a note of it. You know, some time back a space probe by name Rosetta was launched to study the asteroids in the space between, let us say, Mars and Jupiter. Jupiter is a large planet, and the space between Mars and Jupiter had a number of asteroids, and therefore this particular space capsule Rosetta was used to study a particular asteroid by name Steens. Now Steens has let us say has a mass of the asteroid Steens is around 1.208 into 10 to the power 11 kg. you know, the asteroids are somewhat loose material and they do not have a particular fixed path in space, and therefore they wander up and down, and the interest was to bring this space capsule Rosetta as near to Staines as possible, and the nearest distance it came near to this asteroid Staines was something like 800 kilometers. Therefore, we would like to know, when the space capsule Rosetta is 800 kilometers away from this asteroid Staines, what is the attractive force exerted by this asteroid on this Rosetta. Therefore, mass of this space capsule, namely Rosetta, is around, I think it is around 500 kg. We take it as 500 kg. The nearest distance between the space capsule and the asteroid is 800 kilometers. Therefore, what is the force which the asteroid exerts or pulls the space capsule? We say F is equal to G, mass of the asteroid, into mass of the space capsule, namely here it is Rosetta, divided by r square, which is equal to the gravitational constant is 6.67 into 10 to the power minus 11. What is the unit? Newton meter square by kilogram square, into the mass of the asteroid, which is 1.208 into 10 to the power 11, mass of the space capsule 500 kg, and this is divided by the distance square. The distance between the two is, let us say, nearest position is 800 kilometers, and the diameter of the asteroid can be assumed to be 1200 kilometers. Therefore, the total distance of the from the center of the space capsule to the center of the asteroid to the center of the space capsule is 600 plus 800 into, this is kilometers, into 10 to the power 3 square is meter square, and therefore we are getting a force of the order of 6.670 let us say, into 10 to the power minus 11 into 1.208 into 10 to the power 11 kg over here, and into 500 divided by 1400 into 1000 square, and let us take a look at the units. It is Newton meter square by kilogram square into kilogram into, this was again kilogram over here, kilogram square, denominator is meter square, and therefore we have so much newtons as the attractive force. When I look at it even without solving, I find, well, I have a large number here, and therefore the type of force what I get is of the order of 10 to the power minus 6 of a Newton, which is something like a micronewton. That means the attractive force exerted by this asteroid on this space capsule is something like a micronewton, but in space even small forces are of interest, and therefore we find that weak gravitational forces attract the space capsule. However, if we had something like an asteroid over here, and we could have a massive, very massive satellite, like what I said as a gravity tractor, then in that case, if it is really massive, I could pull it with a much larger force. Having said that, let us now see what is the gravitation. What do we mean by gravity? You say acceleration due to gravity. What is acceleration due to gravity? How would you define it? How would you define acceleration? What do you mean by gravity and what is acceleration due to gravity? How to define it? Let us say whenever we do some problems we say force is equal to mg. What is g here? How will you define it? Because all of us know well g has units of meter per second square, we call it as acceleration, but how can earth give something an acceleration? Acceleration is rate of change of velocity. Therefore, small g, how will I define m? We go back to the universal law for gravitation and then we write over here F12 is equal to, let us say I have the earth here, some body is falling on the earth, let the mass of this body be m, let the mass of the earth be me, and therefore the force which this body is pulled towards the earth as per the universal law for gravitation is minus g into mass of this m1 is the heavy mass me, and I have m2 which is the mass which is being attracted over here, divided by, I forget about the vector part of it, I say r square, and r square is the radius of the earth plus the height above the body is the force which is attracting. And what is this force? The force is so much newtons. Now I want to simplify it, therefore I write this as equal to minus g me by re square, and then I write it within the bracket now as m, I put it here, into 1 by 1 plus h by re square, take it to the top, it becomes 1 plus he re to the power minus 2, I expand it out and I know that the height above the earth is very much smaller than re, and therefore I can write this expression as force is equal to minus g me by re squared into mass of the object into 1 minus 2h upon re, higher values, anyway h is smaller than this, I even drop it as a first approximation, and therefore I get the value of force is equal to minus g me by re square into the mass. We just now told ourselves that the mass of the earth is how much? We gave some number 10 to the power 23, 5.974, into 10 to the power 24 kg, and the value of g was equal to 6.671 10 to the power minus 11, and the value of the radius of the earth was equal to 12,756 kilometers 1000 divided by 2 radius square into m minus, which is the value of the force. Now I simplify this, I find out the value of this, and this will come out to be minus 9.81 of m, which is equal to f, and therefore this is the value which is a constant. Mind you, the mass of the earth is a constant, g is a constant, radius of the earth is a constant, and this is what we say f is equal to minus mg. Therefore we are really not telling acceleration due to gravity, we just tell ourselves as per the universal law of gravitation, whenever there is a heavy mass it attracts a lighter mass and it is in a field, that means we are talking of something known as a gravitational field, as it were. And this is the same thing which happened when an asteroid is going, I create a heavy mass here, it deflects the asteroid and I make it go elsewhere. Maybe we should do some problems relating to that, but all what I want to tell you is force is equal to m into g, g has units. Let us see what is the units of g. We put the expression down. The value of g, the constant g was equal to Newton meter square by kilogram square into the mass of the earth in kilogram, radius of the earth by meter square gets cancelled, kilogram comes here, you have Newton per kilogram, Newton is equal to kilogram meter per second square divided by 1 over kilogram, and this is equal to meter per second square. Therefore, the unit of the gravitational field, it so works out, comes out to have units of acceleration, and therefore, many people refer it as acceleration due to gravity, whereas it is just a field due to a particular mass. See, so far we have not said anything extra, we just told maybe the astronomer Johannes Kepler had the 3 laws for planets going round the sun, as it were, sun at a foci and the planets going round it. Maybe Newton saw that he was able to relate that the planets were freely falling towards the sun, just the same way an apple is falling, and therefore he formulated this particular law. We also told ourselves it is based on observation, and since it is based on observation, the law is not something which is really universal, but it is based on phenomena or phenomenological law. We also talked of quasars, which are some bodies in space which travel at a speed near to velocity of light. When those things are traveling at such high speeds, the law breaks down and the universal gravitational law is no longer valid. Therefore, whenever we base anything on observations, the conditions of observations must be related to the particular law, and we tell ourselves, well, I can use these laws only under conditions in which we are talking of masses separated by distance, we are talking of low velocities, and only for those conditions is the law valid. Let us keep it in mind. But still we have not really told ourselves anything about how this law, how will you justify that a heavy mass can attract a lighter mass? How can you justify? Can we do an experiment to show that? And who is the person who did some experiments and showed the validity of the gravitational law? Still it is not proven. We have scientists, maybe some very famous scientists like Stephen Hawking. He has recently published a wonderful book known as the Grand Design. He talks in terms of a unified model for explaining the laws of nature. In fact, in this particular book, maybe the Grand Design, he talks about the phenomenological theories of Newton, then he goes ahead to Einstein's theories about and also about the pioneering work of Feynman. Maybe it will be nice to read through, but all what I wanted to say was, well, Stephen Hawking has looked at maybe the forces in nature, and he has also contributed to evolving the reason why such forces exist in nature. And these people are trying to prove how this law comes through, but can we express it? You had Einstein who gave an explanation for it, and the explanation given looks to be easily understandable, because we should be able to get a force from gravity. Let us try to see this. Supposing I hold something like a towel or a rubber sheet, something like this. I hold a rubber sheet like this. In the center of the rubber sheet I put an iron ball. What is going to happen? The sheet is going to come here, the heavy ball is going to come over here. Now I put a small ball here, it will roll towards it. That means this heavy ball creates a field which helps in the motion of this small ball, and this is an analog to how a gravitational field can exist. But one has to really go through some theories, but the reason for a gravitational field is still not understood. We can only understand it through an example like this. Maybe when I have a heavy mass, I have something like a gradient, and that gradient attracts a smaller mass. Therefore, now we ask ourselves one last question. Yes, in today's class we have been looking at maybe some parameters. We looked at the gravity, gravitational constant, and can we do some simple problems of forces and maybe think in terms of rockets using these forces. You know, there is one problem which I did not bring out to you earlier. The problem is, when I have the earth as it were, and I see an object travelling at a particular velocity v, or some object which is travelling, I cannot define the velocity now. I am on the earth is rotating, and when earth is rotating, I am also rotating along with the earth. That means I am also moving. My velocity of movement is something like 0.46 kilometers per second. This is the speed with which I am moving. Because you have the earth, we said that the radius of the earth, it rotates once in 24 hours. This is the speed with which I am rotating. Now, if I am rotating at 0.46 kilometers per second, and as I am rotating, this body is moving, how do I say that, how am I able to relate the velocity of this body with respect to me? It is going to be difficult to even determine a velocity. Therefore, we have this problem, and therefore, I need to have something like a frame of reference in mind. How do I define a velocity? Under what conditions will the velocity be correct? You will immediately tell me, well, if I am absolutely stationary, like for instance, I am standing here, this is my coordinate system, maybe I stand over here, I am absolutely stationary and a body is moving, then I can say the distance travelled divided by time gives me the velocity. But if I am on a plane like this, and what is my speed? Mind you, 0.46 kilometers per second will translate into something like 1600 kilometers per hour, which is going to be faster than the fastest car which can travel. That is the speed with which I am moving. Now, how do I find out this particular velocity? See, I am also moving on the surface of the earth as an object is moving in space, and my appreciation of the distance travelled by him depends on my movement. Therefore, we are all relative, and therefore, we need a frame of reference to be able to describe the motion of bodies in space. Therefore, to be able to do, I must either be totally stationary, which is difficult, or else I must also tell myself, if I am not stationary, if I am moving at a particular constant velocity, supposing I were to move at some constant velocity and I am observing a body at a different velocity, the change in velocity of this with respect to my constant velocity will always give me the same change. Therefore, my frame of reference, whatever I consider, must either move at constant velocity or be stationary. Then only I can say what is the change in the velocity of this body. Otherwise, if I am here on this earth and it is rotating and all that, my translational velocity is continually changing, I cannot really monitor the change in momentum or change of velocity here, and a frame of reference which is either stationary, let us write it down, which is either stationary or moving at constant velocity is known as the inertial frame of reference. It is very essential to have this distinction very clear. I will come back, all of you are from combustion and background. I will ask you a question, what is the difference between flame speed and burning velocity? Are they the same? What is the difference? No, frame of reference is extremely important in any engineering problem. That should give you a clue. What is the difference between flame speed and burning velocity? Let us do this problem, even though we are getting away from what I should be doing here. Let us say I have a tube filled with gases, and that is what many of you all are doing. I ignite the gases, I allow the flame to propagate. What gives me burning speed or burning velocity? What gives me the flame velocity? I slightly complicate the problem. I tell myself, well, I am standing here stationary, because this fellow is also rotating at the same speed on the surface of the earth, I am also on the same speed, and now I observe it from here. I call this velocity as flame velocity. But if I were to sit over here on the flame and find the velocity with which the gases are coming towards me, I call it as burning velocity. What is the difference? What is the difference? What does it have done? Should it still be the same or should it be different? Now I pose this question to you. I have the tube, I have the gases which are, this is the flame is pushing the gases ahead of it, the gas has some velocity over here, and therefore by the time the flame comes over here, the gas is already in motion, it has a particular velocity, and then the velocity of the flame front is with respect to the velocity of the gases over here. Whereas when I look at the flame from outside, I am looking at the gas as it were moving in this. That means I am looking at the speed of this flame is moving, and around this the flame is moving. Therefore on stationary flame I have, that means I look at the velocity of the gases plus the burning speed over here. That means the flame speed is the velocity with which the gases are moving plus the burning speed here. Therefore they are going to be totally different. Therefore we have to be clear, the frame of reference is extremely important. If I sit on the flame, what I observe is the burning speed, whereas if I sit on the ground and watch something moving, I have something which is the flame velocity. So also the frame of reference is something, and we have to consider only the inertial frame of reference. And the very fact that we are here in a rotating frame of reference introduces new components, and it is necessary for us to compensate for this, and this is what I will be doing in the next class. To summarize then, what is it we have done so far? We looked at the parameters describing the motion in space, we looked at the constituents of space, we talked in terms of planets moving round the sun, we told ourselves the planets are in a state of continuous fall onto the sun, and they are something like a freely falling body, and therefore Newton saw the commonality between a freely falling body like an apple onto the ground and the planets, and then formulated the universal law for gravitation. We looked at the value of G, which we say is the gravitational field. What is the force in a gravitational field is what we told ourselves, and towards the end we looked at maybe the frames of reference, and we said that to be able to measure momentum or momentum change, it is necessary to have an inertial frame of reference. I continue with this in the next class. We will get into a rotating frame of reference, what are the corrections required, and that will help us to define orbits and also the requirements of rockets. Well, thank you then, I think that is it.